Thank you, Jan. So, hi, everyone. I'm Jan Pautrat from Université Paris-Sud. And first of all, I'd like to thank the organizers for the invitation and for setting up this very nice conference. And take advantage of this to thank the organizers of the whole thematic program, which is extremely interesting. So today, I'm going to tell you about invariant measures for quantum trajectories. And now is your last chance to let me know if my writing is too small and you can't read it. Okay, seems fine. So this is a joint work with 3 persons. One of them is in the room. That's Tristan Benoist from Toulouse. And 2 of them are not. That's Martin Fraas, now at Virginia Tech, and Clément Pellegrini, who is also in Toulouse. And so I'm going to talk about invariant measures for quantum trajectories. And just to summarize quickly the outline of my talk, I will first talk about the model itself, that is what quantum trajectories are, and formulate my problem in mathematical terms. Then I'm going to tell you about previous results, what was known so far about quantum trajectories, give you a statement of our results, and maybe, but, well, let's see. Maybe I have time to tell you a little about our proof, because I like it, and talk, of course, about, open problems and perspectives, which might be the more exciting part about this. So, this is tableau 2. No, this. Nope, wrong one. Sorry. This is it. Okay, so that's very high up. To start with the model and discuss what quantum trajectories are. So in a word, quantum trajectories are what happens when you look at a fixed system and get it to interact with a chain of outer systems, which we call probes, and you measure something on the probes. So in all of my talk, the finite system, which will be described by, a finite dimensional Hilbert space, CK. It will initially have a state which I call rho 0, and that's it, essentially, for it. And each of my probes, I will say later why I mention each probe, there will be more than one, has a Hilbert space which is also finite, but is irrelevant. So call it CK prime for the moment. It will not appear afterwards. And say an initial state psi. And I'll say that both of them will be coupled through an interaction which is described by a unitary operator U, acting on the product of both Hilbert spaces. So my picture here is I have my system, which initially is in state rho 0, and have a probe, which initially is at state psi, and I couple the two by my unitary U. So here, more than one thing can happen. Say, in the first case, I just get my system to interact with the probe. And then, let me just denote D for discarding the probe. It's well known that if you do the interaction and then discard the probe, then the new state of the system will be something which I call, well, I can call it the way I want. It will be something which, just write this once and for all, will be written as a trace over my probe, because I will forget what happened to it, of the interaction applied to rho 0 tensor psi, u star. So this is the evolution of the coupled state after the interaction, and this is because I forget what happens to the probe. And it's well known that this takes the form phi of rho 0 for phi a completely positive and trace-preserving map acting on states of my small system. Okay, this is fairly well known. Here I'm going to do one more thing, which is I am going to, before I discard the probe, I'm going to do a measurement. So what is my measurement? Is just I have one observable, which I denote M, for example, which I assume is non-degenerate, and I can just assume that its eigenvalues are integers from 1 to n. Actually, I don't care about the values themselves. They're just labels, so that's why I can assume that. And I will just say that, well, if I do interaction, then a measurement on the probe, and then I discard my probe, then what will happen? Well, I will have an outcome for the measurement it will be I with some probability and if the outcome is I, then the new, so the updated state is something which I can write. And here I'm not going to bother writing it in terms of, well, such a partial trace. Actually, I could. It would be just saying, so the probability here would be this trace sandwiched by the projectors, identity tensor, these eigenprojectors of my measurement. It's a bit too long for me to write it. And actually, it will simplify because I know there's a bunch of operators Vi acting on Ck alone, such that I end up having outcome I with probability, which is just this trace. And then if my outcome is this I, then the updated state can be written simply after I discard the probe as rho evolved by these V's, renormalized to have trace 1. Which one was it? There. Got it. And this Vi, well, there's of course a relation between the phi and the Vi's, which is that the expectation, I'm not saying with respect to what, just the average of my new state. So I forgot to say that this, I will denote rho 1. The expectation of this rho 1 is simply phi of rho 0, so that phi appears as the average evolution of my state, well, average over the possible outcomes of my measurement. So if I repeat this, say n times, with identical probes, so what's going to happen? At each step, I'm going to have a measurement outcome, and I'm going to evolve my state, conditioned on the measurement outcome itself. So the outcomes will be a sequence I1, I2, and so on and so forth to In. And I will have a sequence of states, rho 1, rho 2, and so on and so forth, to rho n. What will be the probability of seeing this series of outcomes? Well, if you just iterate the procedure there, it's easy to see that the probability of seeing this precise outcome is just the trace of VIN, VI1 applied to rho 0, VI1 star, VIN star. That's nice. And my states will be, so I will just give rho n, and every time that's rho n conditioned on seeing that outcome, rho n will be, well, precisely this big sandwich renormalized to have trace 1. And well, so this will be my main object. And just to introduce some notation, let me just say that this is what I will denote from now on P rho 0 of my sequence I1 to In. And I will actually denote, maybe I should write it here, Wn to be the random product of the first n v's that are going to hit my state. Well, one more thing I should say about this evolution of this model is that it has a special feature of preserving purity. More precisely, if, so, I mean, I'm going to say a bit more than just the fact that it preserves purity, because the framework will simplify as well in that situation. The thing is, if rho 0 was a pure state, say, projection on the norm 1 vector x0, then all of that simplifies. And actually, you will see that the outcomes will be I1, In with probability, which just becomes the square norm of Wn applied to x0. Remind you that Wn is this product here.
Again, may I interrupt?
Sure.
The way you stated the probability, so these VIs are just the measurement operators, right?
Mm-hmm. I'm going to do this again.
Yeah. So these VIs, they are just the measurement operators.
They're not measurement operators.
Normally, if you have the measurement operators is VI, then that's exactly the outcome probability, and that's new state.
Well, it depends what you call a measurement operator. I mean, it's not just M.
So it's different from M.
Yes, it incorporates parts from U and parts from M, say. And okay, so maybe the problem is I lied at some point, because as soon as I wrote things this way, so actually this way here, when I considered measurements, I implicitly assumed that, and I forgot to write it there, this was tableau 2, that my initial state here was pure. And then the VIs are actually just blocks of my unitary matrix written in specific basis, which enforces a relation which is obvious from the fact that phi is given by the VIs, which is that the sum of the VI stars VIs is just the identity. Okay. So I was saying the outcome, the formulation, the expression, sorry, for the probability of the outcome simplifies to just this square norm. And the states rho j are pure with rho n, say, which is just this pure state with xn given by just wn applied to x0 renormalized again to have norm 1. Okay, so this will be important in the rest of the talk. Let me come back to my actual problem. So in such a model, I have, well, two sets of objects. I have the outcomes and the states. Actually, the properties of the outcomes are fairly well known. In the sense that one has a law of large numbers, one has a central limit theorem, one has large deviations, you name it. So have a law of large numbers, central limit theorem, one has a large deviation principle, and all these are known, for example, I would quote for the large deviation principle, giving the other two results, a paper by Hiei, Mosoni, and Ogawa, which is from 2007, I guess. And then the extension, I mean, this is a large deviation principle for, say, one letter in my sequence of outcomes. That's an extension for words, which is due to Gutta and Van Horsen, which is from 2014. So what happens to the outcomes is fairly well known. What happens to the other object, which is the states, well, not much is known. So by saying not much, I'm not doing justice to the people who got these results. But let's say the results were still unsatisfactory. So what was known regarding, I'm erasing this because I don't have slides anyway. The previously known results were both due to Kummerer and Masson, and there were theorems of two types. One is an ergodic theorem, which dates from, forget, 2006, 2004, this one. Which is that under some assumption, which I'm going to write, which is an ergodicity assumption on the average evolution phi, here somewhere, yes, on the average evolution phi, then the Cesaro mean of the states rho j converges to some invariant state rho inv, and that was p rho 0 almost surely. So I will give you in a second what this assumption is. It contains the rho inv, as you can guess. But just to comment on this, this was a very neat result. I mean, the proof was very nice, but you could not extend it. In particular, it gives you result about averages of linear functionals of the rows, but nothing else. You cannot ask anything about any other functional of the rows here. And, well, so to give you what this, no, how am I going to do this? Because I want the assumptions to stay. So I'm going to write this one here. This assumption of phi ergodicity is simply the fact that the map phi has a unique invariant state rho in, which is the state that appears all the way up there. And okay, so while I'm here, I will write the relevant assumption for the next theorem, which is what we call the purification assumption, which is that the only projectors satisfying P of some V stars. Let me just make sure I get this right. The only projectors such that this product of V's sandwiched by the P's is proportional to P for any sequence of letters I1 to IN. So to end the sentence, the only projectors satisfying this are rank 1 projectors, for which the property is trivial. So this is an important and, well, fairly unclear assumption, which I'm going to discuss later on. And it played a big role because of the second theorem that was previously known, which is the purification theorem, also due to Kummerer and Masson from 2006, this time. And this theorem was that if purification holds, then, well, there's more than one way to formulate it, but one is saying that the von Neumann entropy of rho n goes to 0. That is, that rho n purifies as n goes to infinity. Okay, so these were great results, but they had their defaults, as I was saying. But still, it was a great hint about what to do, because this purification result essentially tells us that, well, asymptotically, everything will be described by pure states. So this gave us a hint that one should look, well, that is, study the process xn since it was the one driving the whole process in the pure state case. Nope. So this leads us to what was actually our mathematical problem. So let's formulate it nicely once and for all. Mathematical formulation of the problem is simply what is the asymptotic behavior of the sequence xn. So if we stop for a second and look at the process xn, well, it's fairly obvious that it's a Markov process. When you ask most probabilists about how to study a Markov process, they will tell you something like it's all in maiden tweedy. But this process is not. Why? Well, it will probably become clear in the rest of this of the talk. But I mean, just to give you an example, you have a process which acts on a unit sphere, which is such that starting from one given point, you can only go to a finite number of points, which are the effect of applying one or the other cross map. But on the other hand, we have many examples where it seems that the asymptotic distribution of xn will cover the whole sphere. So it's not, I mean, it doesn't fit into most of the categories of Markov chains that was studied in the literature. Still, it's a Markov chain, so the natural questions if you want to study it would be, does there exist an invariant measure so here the answer is extremely simple to give. It's yes, because of the Markov-Kakutani results, and because it's fairly obvious that the transition probability we're going to define afterwards, and which is implied by what's before, is failure, then we know that there, I mean, and because we're working on a compact set, which is the unit sphere, we know that there exists an invariant measure. That's fine. The question is it unique? Last question is, I mean, even if it's unique, we don't know a priori if we have convergence in distribution to it. And well, just to finish with the mathematical formulation, because I have the questions, but I have not actually formulated what are the objects I want to look at. Let's just repeat this, that xn is a Markov chain on the unit sphere of Ck with transition probabilities given by, well, if I start from x, which is in the unit sphere, and I looked at a Borel set, so which is a Borel set, again, of the sphere. Then this transition kernel will just be given by my different cross maps. And can be written like this. So I have this probability of applying this transition. So a probability of ending in set A is given by this. Okay, so because I'm looking at a Markov chain on the unit sphere, I should assume that my initial distribution, that my initial point x is not fixed, but random. So one should assume that x0 can be distributed following, say, nu, a probability on the unit sphere. And then, well, I will introduce some notation by making more precise it's gone. By saying what the probability of observing say a set A, which is again in the Borel set of the sphere, and then observing the sequence of outcomes I1, In. This, for nu such probability on the unit sphere, should be given as the integral over A of these probabilities of observing I1 and In starting from X, average over X. That is, it's like saying I will first sample which X I'm starting from. That's done with probability nu. And then I have the same probability of seeing outcomes I1, I2 to In as before. So I introduced this notation. Observe that there is something particular about this notation in relation to previous objects, which is simply that, well, okay, I'm going to miss space. Which is simply that this P nu, if I look at it over the whole sphere, and I then look at the probability of seeing this sequence of outcomes, is simply of the previous form. It's a P rho probability for rho nu, which is just the average of the possible pure states if the vector is distributed according to nu. Okay, so now that all the notation is introduced, I see some people frowning. The probability is gone. It was below, so there's no chance for me to show it again. Just remark that if you don't believe me here, then this is just integral of the whole sphere of some norm square, which I can also write like this. And then linearity helps me to put the integral inside the trace, and I recover this. Okay, so now that all objects are here, I can state our theorem. Which dates from this year, in which, the paper you can find on the archive. And the theorem is that if both of the above assumptions from the previously known theorems hold, then, well, first of all, to give a short statement, there exists a unique invariant probability measure for pi. And second, to give a more qualitative result, there exists an integer m and two constants c and lambda such that the Wasserstein distance between some average, which, okay, you might ignore, and I will tell you how to view it in a second, by mn plus r. So it's nu this, and nu invariant this. So essentially, this Wasserstein distance here goes to 0 exponentially fast with some rate lambda. Okay, so this might look a bit obscure. I'm going to say something absolutely obvious, which is just that this sum is simply nu pi to the n if m equals 1. And you might want to look at it this way. So let's keep this here. Sorry?
The fact that the Wasserstein distance goes to 0 between invariant measure, you don't quite get a feeling of the first term. So two measures are coming close to each other. What is it?
I'll come to it, actually. You might just want to think of the situation where m equals 1. And then the nu pi n is just the distribution of xn. And, sorry? No, not always, but we can control the m. I will tell you in a second what the m is, and you can restrict to situations where m equals 1, in which case the theorem is more readable. Okay, so since I'm running late, I will try to restrict the number of remarks I'm making. And in particular, I will not recall what the one Wasserstein distance here. Let's just say that, well, say, for example, nu pi n, as we were saying, is the distribution of xn, and that having the Wasserstein distance between two measures going to 0 is equivalent here, because we're on a compact set, to mu n going to mu in distribution. I mean, okay, so the theorem tells me, in particular, if m equals 1, that xn converges in distribution to a random variable with distribution nu invariant. Okay. Question about the m. Well, the m comes from the spectrum of phi. I mean, under the general assumptions that we have, the spectrum of phi is a bunch of eigenvalues which are smaller than 1 in modulus, and then a subgroup of the unit circle. In my picture here, m equals 3. And I mean, I can just assume, because I can just iterate phi sufficiently many times, so I can restrict to subspaces so that phi equals, so that m equals 1. So if the unique eigenvalue of phi with modulus 1 is 1. What other remarks do I want to make? So I want to make 1,000 remarks, but I can't. What about the assumptions of the theorem? So we have two assumptions in there, phi ergodicity and purification. What happens without one or the other? If we take purification without phi ergodicity, then the above theorem doesn't hold as it is. But we have a complete classification of the invariant news. And they're just a convex set with a finite number of extreme points which are related to the invariance of phi. If, on the other hand, we take phi ergodicity without purification, well, there's not much we can say. There is at least one invariant measure. We have examples where phi ergodicity holds and purification doesn't, where we have only one invariant measure. We have examples where we have an infinite number of invariant measures. And we don't know what happens up there. One thing I haven't said, because I mean, we've shifted our interest from the rho n, from the original picture, to xn, is that, let's add it here, the theorem, okay, so either the theorem implies, or I should say the proof implies also convergence in distribution of rho n to a pure state with x sampled from nu invariant. What else do we have? So I will not talk about the proof at all. But let's just say that we have, in addition to this, we obtain a more general ergodic theorem. If you want to state it in terms of, I mean, the same words as was done by Kummer and Masson, we would have something like this. for example, for any continuous function, say, on a set of states. We have central limit theorems for Hölder functions. We can, under some additional, small additional assumption, we have existence of the Lyapunov exponents and we know that the first two are larger than 0 because they're larger than minus log of the lambda that we have up there. But to make negative remarks now, or to open perspectives, we don't have a good control in general of the lambda, apart from this, which doesn't tell you much. Most of all, and I will finish with these comments, we have no information about new invariant apart from the fairly obvious relation, which is that the invariant state rho is the average of pure states with a vector sample from new invariant. And what else should I say? And we have no good characterization so far of the purity assumption despite its very simple formulation. Okay, so I'm afraid my time has run out, so I will stop here.